So in this lecture, I want to look at sort of a sea change in the way that we think about building values. A lot of the course has talked about the importance of structural engineering and materials. And today I want to look at the shift that happens really in the sort of late 20th century, but especially in the 1970s, where the largest problems facing us as a building species seem to be less about building taller or building bigger or building lighter and more about building more efficiently, in particularly in the way that our buildings at first use energy, but also in the way eventually that the processes that we use to build those buildings use energy as well. The term of art today is sustainability. That term is kind of a loaded one, but I think it is probably the best one for thinking about the kind of broad arc of our interest in the ecological impact of our buildings. I think you can date the sort of international consciousness of the fragility of our planet, the fragility of our ecosystem, and the way that our built works and the way that our networks that we've constructed for ourselves either damage or contribute to the health of that ecosystem from about 1968, when this photo taken by Apollo 8 of the quote-unquote pale blue dot, the Earth very fragile against the blackness of space, and the bleakness of the moon in the foreground, really struck a chord with people all over the world in thinking about just how tall or small our planet actually is, and especially how fragile and how kind of insubstantial it seems, the atmosphere in particular. Over the next 10 years, a number of incidents also drove home the fact that the way that we get around, the way that we house ourselves, the way that we provide for ourselves had gotten maybe out of control, and that the amount of energy that we were using, but also the ways in which we were harvesting that energy or extracting that energy were proving harmful to the environment in ways that simply wouldn't allow our species to continue the way we had. There's a kind of slow acceptance of this and also a slow understanding of how exactly we could change the way that we build in particular to address these. There are two moments in the 1970s that drive this home economically. So it's not just a kind of moral or ethical ideal. It becomes a really pragmatic one in 1973 and again in 1979. There's a financial crisis in 1971 that is compounded by the 1973 Yom Kippur War, which leads to instability in the Middle East, and that October, an embargo from the oil-producing nations to European and American markets. The price of oil quadrupled. It really paralyzed America in particular, leading actually to rationing of gasoline. You literally weren't allowed to buy gasoline, depending in some cases on whether your license plate was odd or even, throughout the winter of 1973 and 1974. This was a huge shock. Oil had been easy to come by. We had become a nation that relied almost entirely on automobiles, other internal combustion engines to get ourselves around. And that shock was something that raised consciousness from the pocketbook out, sort of. We saw that there were subsidies for oil that were put into place, so the price of oil was kind of limited, and there were energy standards for the first time put into place for automobiles in the United States. We saw what has now come to be known as lifestyle legislation. So for a while, there was a national speed limit of 55 miles an hour, and daylight savings time for a few years was instituted year-round as a way to try to limit the amount of energy that the country was producing. None of these, of course, were more than a drop in the bucket. And parallel to this, there was a great deal of investment in America in trying to find new sources of energy, but also ways to grow more sustainable resources. In 1979, again, due to political turmoil in oil-producing countries in the Middle East, we saw another oil-related panic when production crashed because of events in Iran and Iraq. And again, gasoline had limited availability. Here, again, we saw a push toward more energy efficient vehicles, but not quite the emphasis on the use of energy in building. Fairly shortly after that, though, in the 1980s, there was a recognition that buildings had a huge role to play in how countries, how societies used energy, how they harvested energy, and how they put it to work. And the energy shocks and the kind of economic, the social impacts that they had gradually made countries, professions, consumers aware of the fact that there were choices that sort of had to be made. The move toward green energy in particular was largely a cultural one as well as an economic one. Events like oil spills, this one off the coast of France, and at the same time, formerly clean energy sources like nuclear had accidents like 3 Mile Island that raised awareness that this was a risky proposition. And there's an idea, Myron Goldsmith, an architect that we looked at briefly before, in a later version of his famous essay, The Effects of Scale, pointed out that part of the problem with energy supplies like nuclear energy was that you were putting all your eggs basically in one basket, and that as you relied more and more and more on these sort of overscaled systems, the possibility that something horrible would go wrong was greater and greater and greater. So we faced real choices in the 80s, and among the methods or among the ways of addressing the energy crisis was the idea that our buildings could use less and less energy, that maybe we could, by lessening demand, we could avoid the supply shocks that we'd seen in the previous decade. If you look at the way that the terminology evolved for a long time through the 70s and well into the 80s, there's this idea that you could solve the energy problem in sort of bits and pieces. So there's a lot of research done, for example, on super insulated houses, and that sort of peaks around 1980. There's also a real interest in passive solar that peaks also around 1980. The idea that there need to be holistic solutions, though, that incorporate a wide range of ideas takes off only kind of slowly. And I think this engram, which shows you the popularity of these various terms, hints at that for a long time we're looking at kind of magic bullets. If we insulate our houses better, we'll reduce energy enough to solve our global problems. Gradually, though, this word sustainability, which implies an overall approach not only to individual building systems, but to the ways that buildings perform holistically, and in fact the ways that buildings perform in groups, in cities, in networks, and that there is also a possibility of looking at better performance. That begins to take off really in the late 1980s. And I would argue that that's very much the way we think today in terms of holistic solutions. We see, though, that the interest in energy savings does take off, and it takes off in a sort of grassroots way, particularly in the 1970s. So there are a lot of homeowners, for instance, who get very interested in heating their houses using solar energy. Edward Masria's book, The Passive Solar Energy Book, is a bestseller, and it talks about how to orient your house, how to shape your house, to take advantage of the kind of natural solar energy that's going to hit your site over the course of the day, and then also, of course, over the course of the seasons. Here you see a couple of images from Masria's book. You can see on the left a sort of very typical kind of late 70s passive solar house, and on the right charts that Masria uses to show how even lay people can understand the way the sun moves through the sky, and therefore the way that homes can take advantage of that natural energy flow. There are a lot of experiments in solar housing, some of them more successful than others. It is associated, of course, with the kind of countercultural movements of the 70s. If you can use the sun to power and heat and even cool your home, then you can drop out, right? You can go off-grid. You can build a dome home in Drop City in Colorado as early as the 1960s. Or you can build one of these sort of alternative homes in Texas or in California that use solar energy to power or to heat or to cool much of the home that you're building. These are very, very small scale interventions, of course, and they don't have any sense of the kind of broader implications or the broader problems of energy production, energy consumption as a society. They're reducing the problem of energy use to a very, very almost sort of microscopic scale. Some of these are wildly successful. There are homes that completely heat and cool themselves passively that are built throughout the 60s and 70s. But again, they don't do much to address the overall national and international need to address energy consumption. There are other things, though, that do begin to look at this. We looked at Bucky Fuller and closed our lecture on Fuller and others with his idea of world gaming, of using, in this case, this map that he either invented or sort of borrowed, the Damaxian map, to show how resources have been unfairly distributed or how they're unfairly distributed throughout the globe, and how we could find both political and technological means of better sharing them. And Fuller was profoundly interested in the way that the energy economy contributed to this inequality on the one hand, but also how it might be able to contribute to ways of addressing that inequality on the other. Looking at the problem globally also brought home the idea that building construction, not just houses, but commercial and institutional, industrial building, transportation building, also had a huge, much bigger role to play probably than the individual kind of drop city houses that we saw in the 60s and 70s. Here in 1996, you can see the U.S. Department of Energy pointing out that the way that residential buildings and commercial buildings used energy was very different. Passive solar works well for residential because most of your energy over the course of the year goes into heating it, at least in most of the northern 2/3 of the country. In commercial buildings, though, it's very different. Most of the energy goes into lighting and cooling the spaces instead of heating them. This was true in the 90s. It's even more the case today that we spend more energy cooling than we do heating our commercial buildings. These sorts of realizations that energy use in buildings was complicated and that was tied into much larger networks led to early experiments that really did look at how we might change the way we build or change the kind of formulas for how we build typical buildings to look at reducing those kind of big ticket items. Passive solar works great for residential. In commercial, though, we've got to find ways to bring in daylight without bringing in a lot of solar gain, right? So the balance between lighting and cooling becomes more important. Some of the early experiments in what today we would call sustainable building come in the sort of high-tech movement. Architects and designers and engineers who are looking at building performance and understanding that there is a gradual shift in how we think of a high-performance building from a lightweight structural building to one that really manages its energy more efficiently. One of the earliest large-scale versions of this is Foster Associates Stansted Airport outside of London in the UK, which has a kind of long design and construction history, but stemmed from the realization that looking at the terminals that the British Airports Authority had built in the decade previous, there were fundamental problems with the conception of these airport terminals that went against a more energy-wise method of cooling them, but also of lighting them. The design team looked at typical British buildings where you have kind of long span truss roof structures with mechanical plant on the roof and distribution through the roof, but also through the floor. There's a limit, of course, on how high you can build near an airport. You don't want planes running into your air conditioners. And so that restricts the height of the concourse to about 9 meters, 27 feet, and requires you to access the ductwork through cherry pickers and ladders and things like that, right? All of the ductwork is up in the ceiling, and there's no way to bring daylight through that ceiling. Early on in the Stansted design process, the team wondered what would happen if you just kind of reversed that. If you took all of the mechanical equipment and put it on the ground level where you could access it easily, brought all of the ductwork up through the floor, so there's no need to bring cranes and cherry pickers into the concourse. And then within the planning height limit of a typical airport, using a very, very thin roof, how you could make that roof transparent, right? Bring in natural light to illuminate the concourse below and eliminate the need for a lot of artificial electrical light in the airport terminal. There were some very clear advantages to this: greater headroom, a lighter roof structure, less material, easier access to the mechanical plant below. And what both Foster's and the British Airports Authority realized was that you created a much more generous space. Foster's idea was to collect all of the mechanical systems, the supply and exhaust, but also all of the signage, all of the lighting that would go on when nightfall came, to collect those within these little structural umbrellas. And that would open up the concourse for much greater pedestrian passage. As you can see, there's not a whole lot of openings. There aren't a whole lot of openings in the roof. About 10% of the roof is glass. And with these diffusers that hang down from it, they were able to shut the lights off even during relatively cloudy days and save a tremendous amount of energy that they would have spent on daylighting. So as early as 1991, there is this idea that that energy consumption is something that we should be looking at. We should be finding ways to organize our buildings so that we're using energy less. We're taking advantage of the sun where we can, either for heating in residential construction or for lighting in commercial construction. At the same time, there are new techniques that are coming into play and new sort of political and commercial realities that are beginning to change the way that we think about building. One of the kind of horrifying, but also I think really important sort of parables of this is the Love Canal disaster in upstate New York that occurred in the 1940s, but that was rectified only in the 1970s, and that led to both a kind of new technique in sustainable building, but also to this sort of political problem that we think of today as greenwashing, of corporate interests that have maybe been responsible for some of the environmental problems that we have, using green building as a way to try to rehabilitate themselves in the social sector. Love Canal was a dump site, an illegal dump site that a company outside of Buffalo called the Hooker Chemical Company used to dump a whole lot of toxic waste. A residential neighborhood was built on top of that in the 1950s and experienced really profound health problems, huge incidence of cancer, birth defects, that eventually led to the entire neighborhood being razed, being destroyed, and the canal had to undergo, or the canal site had to undergo extensive rehabilitation in the 1970s and 1980s. The company got a tremendous amount of terrible press for this, understandably, and did two things. One is they changed their name to Occidental Chemical Company. And the second is they built a headquarters in Buffalo that they said was a symbol of their commitment to kind of ecological rehabilitation. Canon Design were the architects. This is 1980, and this is their headquarters building in downtown Niagara Falls, that use a brand new technique of not just heating, but also daylighting. That they claimed was both going to reduce the amount of energy that the building used and make it a more ecologically friendly building. The term green building wasn't in use then, sustainable building wasn't in use then, but this was very clearly a kind of giant environmental machine, but also a billboard, right? Something that the company was using to show that, or to try to show that it was concerned about its reputation and concerned about rectifying some of the damage that it had done. The Occidental headquarters used an early version of what today we would call a double skin. So there's a glass wall on the outside that is exposed to the sun and absorbs as much of the heat and light from direct sunlight as it can. Behind that, there are two layers. There's an inner layer of glass, a sort of storefront glass that goes story to story. And there's a layer of basically Venetian blinds, louvers that can be adjusted to bring in more or less daylight. This was almost purely a lighting scheme, a way to bring in as much sunlight as possible, but to exhaust the heat gain that typically comes with natural daylight. So you can see from the diagram in the middle that air comes in at the base of the double skin. The sun shining on the glass facade warms up the air inside. It hits the louvers and warms the air around it. That air being warm rises, and you can see that there are grates in the catwalks that run at floor levels that allow the air to come up, and that hot air gets exhausted at the top of the building. So what you're getting is all of the daylight coming in and none of the solar heat gain. So you're not taxing your cooling system with a lot of solar heat gain, but you are able to turn off the lights because you're bringing in enough daylight to work, at least during daylight hours. When it gets cold, which it does in Buffalo, those vents can get shut down. The sun heats up the air inside, and the skin now works basically like a giant parka, right? It insulates the building with a layer of hot air around the outsides. It's not a perfect system, particularly in 1980, and the building was criticized for, among other things, having a similar facade on all four sides. This only works really on the south and a little bit on the east and west sides, certainly not on the north. But it's an idea that gets picked up 10 years later when Germany in particular, because of the taxes that they put on energy, is encouraging companies to find ways to save energy in their commercial buildings. Foster & Partners is a leader in thinking about how the double skin can be applied to a broader range of commercial situations. So here in the town of Duisburg, a formerly industrial brownfield site that's trying to reinvent itself as a sort of Silicon Valley of Germany. Foster's early building there in 1995 uses a double skin in much the same way that the Occidental building did, as a way to bring in daylight without bringing in a lot of solar heat gain. There are other experiments here, so using the core of the building as kind of shaded thermal mass, extracting air from that core and using that to supply the offices, so a temperate air supply that's pretty much always there. Other ideas that didn't take off so much, like chilled ceilings, running cold water through pipes in the ceiling to more efficiently extract the heat from things like computer monitors and office workers. These never really caught on because of sort of intractable condensation problems. But you can see the double skin beginning to evolve, not only as a kind of mechanism, an environmental mechanism, but also really as an architectural idea, that the depth of these skins gives the buildings a little bit more vibrancy, a little bit more grain to them than the single curtain walls of the previous decades. You can see too that they're complicated. You have to be able to operate the inner skin so that you can clean the louvers. Dust is a sort of perpetual problem. And of course, having two glass skins doubles the price of your cladding. So there's a trade-off here between the initial cost. Also today we would recognize the trade-off between the amount of embodied carbon in those two skins and a very, very long amortization. It takes a long time for these to pay themselves back. Not quite as long in Germany as elsewhere in the world because energy is expensive. It's taxed instead of subsidized. But in the United States, for instance, the double skin really doesn't become a viable energy system until the late 2000s. And even then, it's sort of economically questionable. Instead, in the United States, there's a kind of tendency in the 90s to look to passive solar ideas to try to use the sun's path in the sky in slightly more clever ways. And this happens especially in hot climates. Maybe the most notable one of these is the Phoenix Library by Will Bruder and Associates that was finished in 1995. And Bruder's idea was to simply organize the building in ways that brought in what he referred to as blue sky light, so sky that doesn't have the sun in it ever, and to always exclude the direct sun from entering the building. So just in terms of massing, Bruder's idea was to put the core functions in these two copper-clad, what he called saddlebags on the outside, that prevents the sun from coming in the morning or the afternoon. On the north side, which you see here, using vertical sails to limit the low morning and evening sun as it comes north of the east-west line and in the summer, but bringing in again blue sky light. So when you're standing inside the library, all you're ever looking at is blue sky. And on the south side, using horizontal louvers to keep the high summer sun out of the building. On the interior, you can see that there's maybe borrowing from Stansted here, porthole windows, porthole skylights that look straight up where the sun never is in the latitudes beyond the tropics, and using those skylights again to illuminate the interior without bringing in a great deal of solar gain. So by the 1990s, there is a growing realization that traditional energy resources are finite, that we are at some point going to reach what's come to be called peak oil, and that our reliance on fossil fuels is going to have to diminish. There's also a growing recognition that burning those fossil fuels has had an impact on global climate. There is legislation, as I said, especially in Germany, that looks not only at research and development, but that also kind of promotes energy efficient design and construction by beginning to raise taxes on energy, both on coal and gasoline, but also on electricity, trying to encourage consumers, particularly large ones, to spend less and less. Even without that sort of legislation, energy costs begin to rise. And with the recognition that oil is harder and harder to extract in particular, both transportation, but also eventually buildings begin to respond to the economics, if not the moral and ethical implications of global warming, at least at first, the economics. In the next part of the lecture, we'll look at some of the techniques that are used at larger and larger scales, how new tools were put to work to assess how energy flows across buildings and across sites, and how again energy performance really became the kind of one of the major pushes of the so-called high-tech movement, a shift from looking exclusively at the structure and assembly of buildings to how they perform over time, over their lifetime, and how they use energy.